Hey folks, so welcome back to another lesson, and today we're really going to move on to some new physics. And I know the titles these voltage dividers, which we did in Nat 5, but we're now going to use them in something called a Wheatstone Bridge. Okay, so the first half of the lesson is going to be a bit of revision, then the second half is going to be new content. So this is us really starting the higher course now. Okay, so a few revision ideas. Current is the flow of charge per unit time. So remember the equation Q is equal to IT, and that it's just negative charge which moves around a circuit. And you can think about it as being like cars going around the racetrack, and each time it completes one lap, it's like it's going one complete lap around the circuit as well. So it's a good idea to have a model because that will help you to understand the ideas a bit better. Okay, this one's the trickiest bit, which is revision of voltage. So remember, voltage, we actually call it potential difference, and I'm going to try and doing that from now on. Remember, I'm quite bad for this because I always use voltage when I should say potential difference or PD. So let's try and use that from now on. So there's two definitions that you need to know. The first one is that it's the difference in potential between 2 points. That's not really an official definition, so I wouldn't really use that one, but we are going to use it in our problem solving a bit later on, so don't worry about learning this one. This one, however, I would want you to learn, which is the energy given to a unit of charge, and it's got units of joules per coulomb. There'll be an equation we're going to do later on that actually shows this definition, but for just now, learn the word definition. Oh, well, we've got the equation here. Work is equal to QV. So Q is the charge. Remember, that's in coulombs. V is the potential difference. And work is the energy in joules. So if you rearrange this for V, you will then get W over Q, which is why we get our units joules per coulomb. Okay. Remember that dimensional analysis technique where instead of putting in numbers, we sub in the units of our quantity, and that will give us the new units for the left-hand side. So here, work is in joules, and it's over the coulombs, the charge. So J over the coulombs is the same as joules per coulomb. So for example here, what's the potential difference? Well, you've got a potential of 20 volts here and 0 volts here. So to get the potential difference, we subtract them, and we always assume the charge is moving from a high potential to a low potential, and that the difference is always given by the final minus the initial. If you can't remember that, think about acceleration, because acceleration is always the final velocity minus the initial velocity. So here, the potential difference would be the final minus the initial, which is 0 minus 20. So it has a potential of negative 20 volts. So don't worry too much about that in the sense that it's got a negative. You can have negative potentials. Okay, next one, what's the potential difference for this case here? I'll just rub this out. So here again, if you imagine that, well, this is your initial, this is your final, and if we imagine the charge went from here to here, what would the potential difference be? Well, it would be the final minus the initial, which would mean it's 20 minus 20. So the potential difference there is 0 volts. Okay, so in actual fact, that charge wouldn't move at all, because if we think about our second definition, potential difference is the energy given to a unit of charge. If it's 0 potential difference, that means it has 0 energy per charge. Okay, and then the final one, again, I'll rub this out so you can see it. What's the potential difference here? Well, again, let's just use the same technique I used before. This is the initial. This is the final. So again, the difference is the final minus the initial. So it would be minus 20 minus 20. So the potential difference here is actually minus 40 volts. So notice how a wee negative sign here can change what happens compared to previously. Now you've seen this before in Nat 5, but these are ideas that we're going to develop and use in higher. So just to summarise, because there's been a lot of learning in this lesson here, we started with a definition of potential difference. Okay, we focused in on the second one to look at how we get that definition using dimensional analysis. We then focused on the first one again to see how we actually calculate the potential difference. Now, believe it or not, that was a Nat 5 lesson which we did over a period. I've now done that in about 5 minutes. Okay, so here's an analogy to help you to understand the idea of potential difference. And there'll be a wee experiment I would do with you in class, but we're not in class, so we're going to just talk about it as an analogy. If Mr. C jumps off the Eiffel Tower, what happens? Okay, death most likely. Okay, because there's a big height, he's going to kill himself if that's in that situation. Very morbid, I know, but we're doing this for physics, folks. What happens if Mr. C jumps off the base of the Eiffel Tower? And in this case, maybe a twisted ankle. Okay, so the key thing there is what determines whether Mr. C will meet an untimely death or twist his ankle? What is the key thing that determines if he's going to injure himself really badly or if he's going to die? And the answer is, in both cases, the difference in height, I know I've spelt that wrong, is the deciding factor, right? And it's the difference in height, okay? The difference in height. The same is true for potential difference. It's the difference between the potentials that determines how big an energy per charge it has, okay? The same is true for gravitational potential energy. We'll look at that in a bit more detail when we come back to do conservation of energy. And so hopefully Mr. C will just have a broken leg rather than being in a coffin. So a wee bit more revision for you. First of all, you hopefully remember now off by heart that this is the rules for voltages in a series circuit. Vs is going to be V1 plus V2 plus V3. This is a new one for you, but it kind of makes sense. The bigger the resistance, the bigger the voltage across it. Again, we did this in Nat 5 actually, but hopefully if you think about the definition, potential difference is the energy per charge. So if you make it harder for the charge to go around the circuit, you must use more energy to get it through the circuit, so therefore the potential difference has to increase. So can you see how we're now linking and developing our ideas in greater depth? So voltage dividers are actually series resistors, but we draw them like this. Okay, so don't get confused by them. Sometimes they'll draw in a wee extra line here and here, and they'll label this as 0 volts and whatever the voltage supply is to show that it does actually have a cell connected to it. And that's important because obviously a circuit wouldn't work without an electric cell. The other way they could draw it is like this, which is the one that you're probably more familiar with if I put the lines in here like this. Again, don't get confused. These two are actually the same circuit. We've just rotated them by 90 degrees. And the way I remember the second line is think of it as being like crossing a mountain. The higher the mountain, the bigger the effort you need to actually cross it. So the bigger the resistance, the bigger the voltage or potential difference it is to cross that resistance. Okay, so let's look at this in more detail. Now this is revision from Nat 5, so remember we label our resistors R1 and R2. Notice I've not drawn in my wee lines at the side, so I'm going to do that just now, so that way you can see the circuits you would get in your questions. Okay, and there are two equations we use for this one, which we're generally interested in the voltage across R2, so it's this one here, the second resistor. And as I said, there's two equations we're going to use. V1 is equal to R1 over R1 plus R2 times Vs. So this is a really quick way to work out how the voltages split up. If you wanted the V2 version, so be careful because the equation sheet only gives you this one. But for the V2 version, you would just write V2 there and R2 at the top, and that's it. Okay, nothing tricky about that. It's just playing around with notation. And we also have this one here, which again just says the ratio of the resistors is how the voltage is going to split up as a ratio. Now, this one here, the second one here, we don't really use that much in higher. This is the one you're going to use more often. So make sure you're aware how to use this equation here. Okay, folks, now let's put that theory into practice. Okay, so with this example here, I would like you to work out what the voltage is across R2. Now, if you recognize this from Nat 5, feel free to pause the video and do it, and then listen in to the explanation, because there's a wee hints and tips I'm going to show you. If you've never seen this before, obviously listen in, and if you don't understand it, play it back again. I want you to appreciate though, just like the previous slide, we did this in Nat 5 over maybe a period or 2 periods. I'm now doing this in about 10 minutes. Okay, so first of all, we draw in the wee bit there, because that really should be in there, which is the lines or the leads that connect to your power supply. So you would have probably 10 volts up here and then 0 volts down here. It's a series circuit because if you think about the current, there's only one way for it to flow. So we know that R1 will have a voltage V1 and R2 will have a voltage V2. Straight away looking at this, we know that R2 will have the smaller voltage than R1. So when I do my calculation, I can check to see if my answer is correct because I know that V1 plus V2 must equal to the supply voltage. So notice how I've pulled together a lot of different physics to help me guide myself to the right answer. Okay, now by this stage you should probably know it's a voltage divider, so we do our KFC technique. So know it, which is write down what we've got. So we know there are 10 volts there. We know that R1 is 50 ohms. Okay, I'm going to miss out the units to make this a wee bit quicker because I appreciate you could probably just quicker on pen and paper. R2 is 25 ohms and we are looking for V2. So know it, find it, exam technique now. You write down your equation as it is in the equation sheet, obviously substituting the V1 for V2 and the R1 for R2 because that's what we are looking for in this case here. And that's multiplied by Vs. So notice my exam technique, I'm picking up 1 mark straight away, and then I'm getting my second mark because I am putting in my numbers. So this is 50 plus 25, and that is multiplied by 10. And then you can work this out on the calculator. Off the top of my head, this will be 25 over 75, which is a third, times 10, which works out to be 3.33 volts. Okay, now can we check if this is the right answer? Well, first of all, if we think about it, if V2 is 3.3 volts, what's V1 got to be? It's got to be 6.67 because remember, these two have to add up to the 10 volts. Is V2 smaller than V1? Yes. So we know our answer's probably correct. And this is what I love about the physics, folks, is if you know your stuff well enough, you can always figure out if you've got the right answer or not. Okay? Hopefully that was revision for you. Again, if you're not sure, go over it again. Okay, now this is proper higher work. If you weren't sure about whether or not we were doing higher. We are definitely doing higher material now. So what is the potential difference given this circuit here? So let's break it down, folks, again as usual. And you can see I'm going to add in the lines where you would connect this to an electrical cell. This would of course be 0 volts, and this would be 10 volts, the supply voltage there. Okay, if we look at the circuit, is it series or parallel? Think about the current. The current comes in and then it splits up into 2 bits. So that means these two are in parallel to each other. But when you get into a branch, it then becomes a series circuit because there's only one way to pass through both resistors here. So this is a really weird circuit because it's technically a parallel circuit with series bit, or it's 2 voltage dividers connected in parallel. So the question then is, how do we work out the potential difference measured by the voltmeter, right? So what we have to do is think about the definition of potential difference. It is literally the difference between two potentials. So to get the potential difference, we need to work out the potential here, which I'm going to call A, and here, which I'm going to call B. Okay, so just like the example we talked about when we did the definition of V. So we already know from the previous example that there is 3.3 volts here. Okay, can't really do my dots because my mouse pad isn't very sensitive at the moment. Okay, so I know there are 3.3 volts at A, and the reason for that is we know that there is 6.37 volts here. So whatever's left has to go after R1. So if R1 took up 6.37 volts, there must be 3.33, no, sorry, that should be 6.67 volts. Then that means there must be 3.3 volts left to go over R2. Okay, so that means the potential is 3.3 volts, or the potential at A is just the same as the potential difference across R2. So B, well, B, we can use a wee trick because we notice this is identical to the other half. So we know straight away that B is also at a potential difference of 3.3 volts. Okay, so we know the potentials now. To get the potential difference, we just subtract them. So if you think about it, the current is coming in from this way. So it's going to go through this branch first, and then it's going to go through this branch. So this is the initial. You could treat this as an initial, and you can treat this as the final. So final minus initial is 3.33 minus 3.33. So after all that chat, folks, the potential difference is 0 volts. Okay, now in reality, although it's new physics, we're actually still using the same ideas. We're thinking about the potential difference. We're calculating the potential across R2, and then doing the same for the other half because we realise they're actually identical. We're then using our definition of potential difference to give us the potential difference by subtracting the two potentials here, and that gives us the answer of 0 volts. Now, what I would do in class is I would show you this with a practical experiment, but I can't do that. So what I'm going to do, folks, is I'm going to make a YouTube video using a simulation to show you the exact same results. Obviously, it's a simulation, so it's going to work, but at least you can see the thing in practice, okay? I'll try and upload that either tonight or by tomorrow. My internet connection is really, really rubbish, so be patient with me on the YouTube video, folks. Okay, folks, so what we actually did there was something called the Wheatstone Bridge. Okay, and the Wheatstone Bridge was developed by Wheatstone, and usually the full circuit is drawn like this. You can see you've got your voltage dividers 1, 2, and 3 and 4, and the voltmeter is connected across it at a very specific point. What is the Wheatstone Bridge used for? Well, before, I guess, they had transistors. they use this as a really sensitive control circuit, because you can imagine that if one of these resistors, excuse me, was to change by a very small value, then that would mean the potential here would change, and so you would get a reading on the voltmeter, and then you could read that voltage and use it to switch things on or off. Okay, now you're not really going to be using these in that sense, but you might find that in problem solving questions, so just be aware of it, and that's why I'm going through this in quite a lot of detail. Right, now, as always, what I'm trying to do with you folks, and hopefully you're realizing this, is I'm trying to distill the physics into a series of steps that you can follow. And as long as you learn the recipe, you will always kind of have a good chance of getting the right answer. And this is where I'm trying to make it a bit more like maths, because I know you guys are really, really into your maths and you're really good at maths. So if I make it a bit more like that, then you will find this subject a lot easier and you'll actually do well in it as well. Okay, so here's a summary of how you solve a Wheatstone bridge. In actual fact, it's the same as the worked example I did before. Notice if you turn your screen by 90 degrees, we've pretty much got the same circuit as the one we did in the worked example. So here is my method for solving Wheatstone bridges. Okay, we treat this as two separate voltage dividers, so that's why I've deleted the rest of the circuits. We calculate the voltage across R2 in general and R4 in general. I'll show you some variations of this later on, but you're always calculating the voltage across one of the resistors, and you're doing the same for the other branch. And then we remember the definition of V. Potential difference is the difference in potential between 2 points. So that's how we do these type of questions. So think of it as a voltage divider, calculate the corresponding voltage across one of the resistors, and then you subtract that answer from the corresponding one on the other branch. You've seen that in action. If you're not sure, go back to my worked example and run through it again. Okay, now one equation which is tied in with Wheatstone Bridge, which isn't in your relationship sheet, is this one here. And this is one you've never seen before. It says R1 over R2 is equal to R3 over R4 if you have the voltmeter connected in this way. Because if you're thinking about it, you're splitting voltage 1 over voltage 2, and that ratio has to be the same as the ratio of voltage 3 over voltage 4. What determines the ratio of voltages? The resistance. So if you wanted to, you could write this as V1 over V2 is equal to V3 over 3V4. But it's fine for us just to do R4 and resistances. So just be aware of that, folks, okay? Now, this is a special case where if the ratio of the resistors are equal to each other like this, then we say the bridge is balanced. And a balanced bridge has a potential difference of 0. So how do we use that idea of the balanced bridge then? Well, it's actually really easy. It's an example is here. The bridge is balanced given what R1, R2, and R3 are, determine R4. So KFC technique, folks, I'm going to write down what I've got. So I've written them down there already for us. But obviously you can do it on your pen and paper. A question mark there. So we know the equation we want to use is R1 over R2 is equal to R3 over R4. Now, let's just check this is the right equation, because if we look at the circuit, our voltmeter is here, so we can see we've split R1 and R2, and we've split R3 and R4, so that's the right equation. It's then just a case of plugging in the numbers, because we know the bridge is balanced, we can use this equation, and we know the voltage is splitting accordingly across these two resistors. So we do 100 over 200, and that's equal to 50 over R4. So if I work that out, I know that R4, you can do that by cross multiplying. You can use your calculator. It's up to you how you do that. R4 is simply 100 ohms. Now, the really nice thing about Wheatstone bridges is you can check it's the correct answer, because if you sub this back in to the equation, you should get the same ratio on both sides. So 100 over 200 is a half, 50 over 100 is also half, so we know it's correct. So again, that's the nice thing about physics, folks. Okay, example 4 now, and um, there's two more examples after this, folks. So if you want to have a break, I know I've been talking about 25 minutes. Feel free to go for a break and then come back to this. If you're back and ready, let's have a look at this one here. So again, the bridge is balanced. Determine R4. Okay, now remember, if it's balanced, we can use our equation R1 over R2 is equal to R3 over R4. So let's check that this is how the voltage is splitting up. So if we look at the circuit, now notice how they've changed it and made it a wee bit harder by drawing the circuit in a different way. This is where your kind of power lines would come in. So this would be your V supply and this would be your 0 volts. So if we look at it, is R1 and R2 splitting the voltage? And the answer is no. How do I know that? Well, if you think about it, is the voltmeter splitting up in between the R1 and R2? It's not. If you look at the previous slide, R1 and R2 was splitting the voltage if the voltmeter was connected in between them. So that means that R1 and R2 aren't actually dividing voltage. R3 and R4 is the same, so they're not dividing voltage. It's actually R1 and R3, and then R2 and R4. So our equation here, it's the right equation, but for the wrong set of resistors. So we have to rewrite the equation as the following. R1 over R3 is equal to R2 over R4. Because remember that this equation describes the ratio of the resistors and the ratio at which they divide the voltages. So you've got to match the equation to the actual circuit. Once you've done that, this is the tricky bit, I would say, you then just plug in your numbers as before. So we now know it's actually 150 over 250, okay? And that's got to equal to 200 over R4. So again, you can cross multiply to get yourself the answer. Okay, I'm just going to do it on my calculator very quickly just now, so you can hopefully see or get the same answer as me. So 150 over 250, and then it's where it gets a bit tricky because I'm not using a scientific calculator. So let's do this a slightly different way. So I'm going to do 200 times 250 and divide by 150 because I'm cross multiplying, and I get my answer to be a lovely number of 333.33. Okay, and remember your units, it's ohms because they're resistances. Is that the correct answer? How do I check it? I plug it back into my equation and I should get the same answer for both sides. So notice we've changed the circuit a wee bit, but we're still using the same technique. We're still using the same theory. Okay, second last example, folks. So again, feel free to pause the video to try this one yourself. This is where you would normally connect this circuit into the electrical cell. So this would be your supply voltage. This would be your 0 volts. So the bridge is balanced. Determine R4. So pause the video and have a go of it yourself. I'm going to take you through the answers just now. So before we do anything, we now know we need to check if the circuit's set up in the way we want to use it. So here, the voltmeter is connected between R1 and R2. So we know for sure that the equation R1 over R2 is equal to R3 over R4. is exactly what we are looking for. So then it's just a case of plugging in your numbers here. So it would be 150 over 200, and that's equal to 250 over R4. Now notice in each of my examples we're looking at R4, but you could be asked to find any one of R1, 2 or 3, and they'd obviously give you the corresponding numbers to get that. So finally we do the calculation. So R4 is the same as, for me, doing it on my phone calculator, which you shouldn't be doing, you should be using a scientific calculator. You do 250 times 200, divide by 150, which again gives me that lovely answer of 333.33 ohms. And again, I can check my answer by plugging this in and seeing that the ratios are correct on both sides. Okay, folks, final example, so thanks for bearing with me. Let's put this all together now and look at this example, which is the one you're going to get, the questions you're going to get in the tutorial is more like these ones. So the bridge is unbalanced, given R1, R2, R3 and 4, pardon me, determine the reading on the voltmeter. Now, if we look at this first, straight away we can see it's unbalanced because we can see R1 divided by R2 and R3 divided by R4 are going to give me different answers. Okay. Secondly, if we look at our circuit here, we can see that the current comes around here. So it's going to go through this bit first. So we're going to call this the initial. And this bit must be the final. Let's double check that the voltages are splitting up between R1 and R2. Yep, because the voltmeter is connected between them. And same for R3 and R4. So notice I'm still using the same processes that I used in the earlier examples. Okay, remember, learn the process and you'll find physics really straightforward. So we know it's unbalanced, so our equation for a balanced Wheatstone bridge isn't going to work, and we're going to have to use voltage division. So let's do voltage division. Remember, we're only interested in V2 and V4, the second voltages. So exam technique, write down your equation. I'm going to skip a step because I know writing the equation for me is a wee bit trickier, and I'm just going to plug in the numbers straight away. So that will be 200 all over 300. Okay, and that's multiplied by 9. Okay, so that should give me an answer of 6 volts. Yep, that gives me an answer of 6 volts. Okay, let's check to see if that's correct. Well, if we look at it, R1 and R2, R2 is bigger than R1, so it should definitely have the bigger voltage across it. V4 now is equal to 50 over 250 times 9. So I'm just going to do that just now so that, because you can see what my writing is going to be. So that's going to give me 1.8 volts. Okay, so I know in my circuit that this is going to be 6 and this is going to be 1.8. So remember, the difference, the potential difference is always the final minus the initial. So it's going to be 1.8 minus 6, which gives me an answer of minus 4.2 volts. And that's it, folks. So can you see how we've been applying the same technique all the way through? Okay, so lots of worked examples to go through, lots of questions for you to try, folks.